All right, everybody, welcome. I think I'm gonna go ahead and get started here. It is another week. It's Tuesday. I hope that you guys had a good weekend. I went all the way to Arizona, celebrating getting done grading the exams. Like, need to give myself a break. So I drove to Arizona. I left here at 3 a.m. on Friday morning. I drove all the way to Tucson because I needed to hike for 4 hours before it got dark. This time of year, it's dark for a long time. And I climbed up through the cactus areas up to a campsite in this national park over there, Saguaro National Park. I camped there, and I really hated being in the tent for 11 hours with total darkness. This is such a long night. Then the next day I got up and I hiked across the highest point in that national park, climbed 2 mountains basically. There's even a little bit of snow there, if you could believe it. And then I went down partway the other way out of the park. So I did not go back to my car. I went down a different direction. And then on Sunday, I hiked all the way back to my car again. And then I took an Uber back to the starting point. I did this all by myself. Sometimes I do these crazy things by myself, just backpacking for 3 days. Got back to my car and I drove to Phoenix. I have a friend who lives in Phoenix, so I stayed there Sunday night with that family and drove back yesterday morning.
Go back.
Thank you. This is what happens when I have 12 hours of teaching on Tuesdays and Thursdays. I have like 4 days in a row to kind of get some other things in between. So that was kind of nice. I hope that you guys also were able to have a little bit of enjoyment after our exam last week. Hopefully you had a little bit of a break. It doesn't last very long around here though, does it? There's so much to do always. Let me just see, do I have any real announcements right now? Not so much. There is homework due tonight. I see one problem has made it onto my board over here. If anybody else would like to add to that list during our break today, feel free to do that because I'll try to save a little time to answer questions on the homework tonight. And that's the homework for this week. I decided with the next assignment to give you an entire week to work on it. We're going to go pretty slow through sections 4.4 and 4.5, which is what the next homework is about. So I want you to have enough time to really do a good job with that. And so that will be due next Tuesday. So you have some time to work on that. Nothing to do the rest of this week. I know I'm in my old age, I'm getting weak. I'm giving you a whole week between assignments here. Anyway, don't get used to it. That's all I can say. But at least for this week, we're going to enjoy that. So yeah, that's kind of all I've got as far as just a logistics and announcements. I do have office hours tonight, just to remind you about that as well. So if we don't get a chance to answer all your questions, or if you're not done yet and you just need more time to work, the place outside my office should be open. I should be there. Or you can come into Zoom and ask me questions that way. Whatever works, but it's a pretty important homework, so definitely give it a good effort if you would. What I've got on the board here, guys, as I always do, I like to come in with a recap of where we kind of left off, especially on Tuesday, because it's been 5 days, and just to get it back into our heads again, we started this idea of vector spaces in chapter 4, this sort of abstract mathematical framework that we can study lots of linear algebra problems with. But as I mentioned last week, it's really the subspaces within those big universes that we usually are more interested in, right? And so I have the subspace idea here. It's really just a vector space within the larger vector space V. And as such, it inherits most of those rules. Remember the 10 axioms of a vector space? Most of those get inherited for free by S from V. So the only ones that really have to be checked, are the closure under addition and the closure under scalar multiplication. Now I also throw in this 0 vector check, which is another axiom, but that's just because that's optional. But I like to do it because if the 0 vector check fails, I can just call it a day and say, nope, it's not a subspace, because every subspace, every vector space has to have a 0 vector, okay? So I hope everybody's not getting confused like I did when I was a student. I got confused. What's the difference between a subspace and a vector space? The answer is there's absolutely no difference at all. A subspace is a vector space. It's within some larger vector space that contains it. That's the only point I'm trying to make here. Okay. Anyway, so last week we practiced a lot, checking closure under addition and closure under scalar multiplication. Keep working on it. How do we write it down, right? What's the notation? You're going to find that takes some practice because, 1 minute you're doing a problem about polynomials, and then the next minute the vector space changes, and now all of a sudden it's matrices. And then all of a sudden after that it's calculus functions. So that's why this homework that you're working on for tonight is a little longer. It's because I really need everybody to practice like how it's going to look, how you're going to write it in many different contexts, right? So anyway, that was a lot of what we did last week. We had that group work that we did that has a whole bunch of examples in it as well that you can kind of review as well. Towards the end of class though, last Tuesday, we started talking about what I'm going to pick up with now today, which is turns out there is a very cheap way to make subspaces, to make vector spaces within a bigger vector space. All you have to do is grab a handful of vectors out of your vector space. No rules about which ones you can or cannot grab. Just grab as many of whatever vectors you want out of your vector space. I'm going to call them V1 through Vn. And again, this could be any of our vector spaces. These could be polynomials, these could be matrices, these could be functions, right? And what you do with those vectors, guys, is you form their span. You form their span. You take the span of those vectors. We're going to see this thing a lot, right? And what it is you're basically closing up the vectors under addition and scalar multiplication so that it becomes a subspace. Look at the theorem at the bottom. The span of any set of vectors whatsoever is always a subspace of V. It's a cheap, easy, guaranteed way to make sure you have a subspace, right? So that's really nice. It turns out we can make millions of them, right? Everybody in this room could grab a different handful of vectors, take their span, and have a different subspace of V, right? There's lots of subspaces. And just to remind you again, the span is essentially what are called the set of all of the possible linear combinations. This is where you're doing the two vector space operations, which are addition and scalar multiplication, and you're just building all of these expressions. You're saying, look, I need it to be closed under addition and under scalar multiplication. So the way we're going to do that is we're going to take our handful of vectors that are probably not a subspace just by themselves, and we're going to throw in all of the linear combinations of those vectors as well. And by doing that, we get a much larger set that is now closed. It does form a subspace of V. Okay, this is kind of the idea of taking a span. All right, so I would like to warm up maybe, since it's been 5 days, with a couple of warm-up examples, if that's all right. Are there any questions so far over here, though? It's just kind of summarizing what we did before. Let me give you maybe the questions will come if I do a little warm-up problem. Feel free to let me know if there are any questions here. Let's just warm up a little bit with this because it does take a little practice here. So I'm going to go ahead on this middle board and write down, we're going to do 3 warm-up problems. For the first one, I'm going to let V equal P2 of R. Okay, and then what I'm going to do is I'm going to let S be the set of AX squared plus BX plus B minus A, such that A and B are elements of the real numbers. Now, you may not recognize that immediately, but actually this was one of the items on the group work from last week, group work number 6. So maybe I should just make a note here. C, group work number 6. I believe it was part D. That some groups, it might have been part E, I'm sorry. It's either D or E. I think it's D. Yeah, it's part E. Not every group that was working last Thursday had time to work on this one, so I thought, well, let's just do it together. What were the group work questions asking? It just said, is S a subspace of V? So is S a subspace of V? You can see that, remember, P2 of R, this is the universe of all quadratic polynomials, right? This is polynomials of degree 2 or less, so anything in V should be looking like a quadratic polynomial. And sure enough, if you look at the expressions that I'm giving you for S, it looks like a quadratic polynomial, the form of some kind of a quadratic polynomial. So at least it makes sense, right? This should have the right form. But the question is it a subspace of V? Now, the way we would have done this problem last week is we would have first said, is the zero vector in the set? It turns out the answer is yes, because if you allow A and B both equal to 0, by the way, we're not plugging in for X here, we're plugging in for A and B. If we allow A and B both equal to 0, what you see is you get 0x squared plus 0x plus 0. That is the zero vector. So it passes the zero vector check. And after that, if we had been doing this problem last week, we would have next looked at closure under addition and closure under scalar multiplication, right? I'm going to do it differently right now, okay? I'm not going to go back to the previous stuff again where we would go through those two-step process. I am going to show you a different way to get the answer is yes, okay? How am I going to do it? I'm going to express that S as a span, because my theorem says that anytime you take the span of anything, right, it is always a subspace. On our next midterm, I'll probably have a question that'll have a few parts. It'll say, is S a subspace of V? Over and over and over again. If you see a part on my next exam where the S is written out as span of whatever, it doesn't even matter what the whatever is, right? If it's the span of anything, you just circle yes, and you basically are gonna know that I was giving you guys a gift, right? It's an easy one. A span is always a subspace. And I'm gonna show you that this is a subspace by expressing it as a span. Are you ready? Let me show you how we can do that. So here's the reason. S is, so you see what we have up here. This, let's take a look at this polynomial expression. I am going to just do a little algebra with it. I am going to bust out the A from everywhere that I see an A, or in other words, I'm going to factor it out. If I factor out the A, you see that I have an x squared and a -1 on that, right? And then I'm going to do the same thing with the B. I'm going to take out the B, and I'm going to look at where do I see the B up here, and I'm going to factor the B from those terms. There's an x and then a +1 on that. What is written right here, my friends, is literally the same thing as what's circled on the original question. And this is still, the same little conditions here. A and B are real numbers. But guys, if you look at what we actually have right here, doesn't that look like C1 times V1 plus C2 times V2? I realize it's A and B, but those are just numbers, the same way that C1 and C2 are just numbers. And these two polynomials that are in the parentheses, those are vectors in my universe, right? This is literally just the span of, and now I list out the x squared -1 and the x plus 1. And that justifies saying that we have a subspace. Anytime we express our subspace as a span, or anytime we take our set, and if we're able to express it as a span, well, then it is a subspace. Remember, span means you're looking at linear combinations of your vectors. Okay, so if I went in and I grabbed these two polynomials, right? I have two polynomials that I grabbed out of V, and I said, okay, I'm going to take their span. First of all, I'll know it's a subspace. And secondly, if I actually write out what it is, all of these linear combinations, it's exactly the S that we started with. Does this all make sense? Okay, so this is going to be an important idea, this idea of sort of distilling down your subspace into some specific vectors that sort of are spanning that subspace. They are the ones that are creating that subspace. So I'll make some definitions here shortly, but at least for now, I just want to get this idea across. Is everybody okay with that? Okay. Let's do another warm-up problem. Let's take a second one. This one's going to be a little different. I'm going to ask you something slightly different this time. So this time I'm going to use a different vector space. I'm going to take V to be M3 of R. Right? And I'm going to let S be equal to the span of, and now I'm going to use my braces and I'm going to list out some 3x3 matrices. Okay, so here's the first one, right? So you have 0, 1, 0, negative 1, 0, 0, and then the third row is 0, 0, 0. And then I'm going to make another vector, 0, 0, 1, 0, 0, 0, and negative 1, 0, 0. And then the third one is going to be 0, 0, 0, and then 0, 0, 1, and then 0, negative 1, and 0. Okay. So I'm giving you a vector space, and then I'm giving you this set S right there. Question for you, is S a subspace of V? Do you already have the answer? Yes, because it is a span. Anytime you take the span of anything, it is always guaranteed to be a subspace. So I already know it's a subspace. Unlike over here, I had a question. Is it a subspace, right? Here, it's like already a done deal. It's a span, so it's a subspace. Now, the question I want to ask is, what is S? I actually want to know, like, what is this thing? If I take, like, all possible linear combinations of these vectors, do you think you might know, Anthony?
Yeah. Together, so B 0, negative negative.
So you're giving me like the general form of what we would have. Yeah, basically what I'm gonna do, guys, is I'm gonna take all possible linear combinations of those three matrices, right? So the answer here is exactly right. Anthony's got the idea here. S is really just going to equal the set of, okay, instead of C1, C2, and C3, which are the constants I'm using in my generic introduction over here, I'm gonna use A, B, and C. So I'm gonna have A times the first matrix, right? So I'm building linear combinations of these vectors, right? It's a closed up set under addition and scalar multiplication. Then I have B times 0, 0, 1, 0, 0, 0, negative 1, 0, 0, right? And then plus C times 0, 0, 0, 0, 0, 1, 0, negative 1, 0. Sorry for all the writing. Takes a little while to write all that out. And then this is going to be such that A, B, and C are real numbers. Okay. And if you want to, guys, I'm going to do one more step on this one. If you want to, you can compress this down into a single matrix. So you can put the A on the inside, you can put the B on the inside, and you can put the C on the inside, and then just add the term, add those together, right? What you will get, I'm going to go ahead and do it for you here. What you will get is 0AB, negative A, 0C, and negative B, 0, negative C. Again, this is such that A, B, and C are real numbers. I screwed something up. I sure did. Thank you. Oops, that should have been negative B, negative C, and then 0 on the bottom right corner. Exactly, just like that, right? Does everybody see how I got that? I just multiplied the A into the first matrix, so that put an A and a negative A here. And then I have a B and a negative B. And here I have a C and a negative C, and I just added it all together. I just get this one final matrix here. And what I'm looking for, is there anybody out there that wants to tell me what kind of a matrix that is? It's skew symmetric. It's skew symmetric, right? It's the one where it's kind of symmetric across the main diagonal, except there's minus signs on one side, and you have to have zeros on that main diagonal. So guys, let's just add one more line here. This is equal to the set of 3 by 3 skew symmetric matrices. And guys, what this is doing for us is it's giving us a second way of proving that the skew symmetric matrices form a subspace. That was also in the group work last week. That was also in last week's group work. So I'm just going to make a note here. C, group work number 6. And this one I think was part B. Now, when you did it last week, you probably were, you checked closure under addition, closure under scalar multiplication. I now have a new way to explain why the 3 by 3 skew symmetric matrices form a subspace, and it is that those matrices are the span of something. Anytime you take the span of anything, you always have a subspace. I'm going to say that about 20 times. Make sure everybody's got that one down. This is all good? So that's kind of nice. So we have a way of getting around having to check closure under addition and scalar multiplication all the time. If we prefer, we can try to figure out how to write our set S as a span, which is exactly what I just did right here, right? And we could have done this kind of in reverse. I could have started you off with this form here and said, here's S. Is it a subspace? And you would have done kind of similar to what you did over there where you factored out the A and the B. Here you would factor out the A, the B, and the C, and you get this. And you say, oh, that's just the span of those 3 matrices. That's a brilliant idea. Okay, so that's a clever trick. Let's do one more. Do one more warm up, and then we'll try to get down to business of what we're really going to try to make progress with here tonight. So on number 3 is going to be kind of like number 2. I'm going to take V to be P3 of R. And I'm going to, so this is cubic polynomials of degree 3 or less. And I'm going to let S be the span of 1x, x squared, and x cubed. And I'm going to ask, what is S? So this is kind of like number 2 in the notes here, in the warm up. Okay. So let's try and answer this one as well. I'll just maybe put the answer right here. First of all, will it be a subspace? Yes. Absolutely. It is a span. As soon as I see that word span, I don't even have to think about it anymore. Yeah, it's a subspace by its very construction, right? When you formed all possible linear combinations, you were making sure that it's closed under addition and scalar multiplication. So you don't have to sweat that anymore. It's like, that's definitely a subspace. So this is a subspace. It is a subspace. The question is, what is it? Like, is it like here we were able to describe S as the 3 by 3 skew symmetric matrices. I wonder what this one is. Let's just look at it. S is going to be linear combinations, all possible linear combinations of these 4 vectors. So A times 1 plus B times X plus C times X squared plus D times X cubed. And this would be such that A, B, C, and D, these are elements of the real numbers here. So what is this actually? This is just expressions of the form A plus BX plus CX squared plus DX cubed. That's what we have. Does anybody want to tell me what that actually is? Like up here, I said I could describe the previous one as 3 by 3 skew symmetric matrices. What would I describe this one as? Andrew? It's the entire polynomials of degree 3. It is exactly the entire universe that we were working inside of. Okay, so the P3 of R was our big universe. I happened to give you 4 vectors out of V. I grabbed those 4 vectors and I formed their span. And it just so happened for this one that when I grabbed those 4 vectors and formed their span, all possible linear combinations, I ended up with the entire universe. That can happen. That didn't happen on the second one. The second one, we only got the skew symmetric matrices. We didn't get all 3 by 3 matrices. We only got some of them, right? But on this problem, we actually got the entire vector space V. In some sense, we could view that as a failure. Because what was the whole goal of this? The whole goal of this was to grab some vectors and create subspaces. Well, if you grabbed some vectors and took the span and you got the entire universe, you didn't really get anything very interesting, right? You just reproduced the big universe that you had in the first place. It's not so exciting, but well, it's exciting enough that I need to make a definition that we need to put into our notes here. Can I write over here, guys? You guys can read that. I'll try to write nice and big for you. Let me make a definition here based off of this example. And the definition is just this. If we take the span of V1, comma, V2, comma, dot, 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 up to Vn. If we take that span and it turns out to be the entire universe, like it did in this third warm-up problem, then we call those vectors, we call that set V1, V2 up to Vn, we call that a spanning set. It is a spanning set for V. A spanning set. It's a set of vectors that when you take the span of them, you get the entire universe of V. Yeah. And we also say, we say that this set V1 dot comma V2 dot 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 up to Vn, we're just going to say that that set of vectors spans V. It spans V. It means everything in V can be written as a linear combination of the vectors. It's like those vectors are the building blocks of the universe. It's like the atoms of the world that we live in, right? Everything in this world is made up of atoms that are put together, right? Those are really important for chemists to study and understand, right? The building blocks of the universe would be like super important to be able to play with. So in this case, I have 4 building blocks for P3 of R. Right, those 4, 1, x, x squared, and x cubed, they are building blocks for P3 of R, which is pretty sweet. So I am ready to state the 2 main questions that we're going to be working on tonight. Unless there's a question. Yeah, Vinny, go ahead. Please. Yeah, good.
Are you able to span a vector that we don't know that it's a subspace? In other words, how do we know that it's not spanning?
How do we know whether our set of vectors will span V or not? Oh, well, that's one of my questions on my little sheet right here. Yeah, I just said there's 2 things we're gonna be focusing on, and that is one of them right there. So you're right on cue. Getting a little worried here. Somebody else is gonna be taking over my job soon. But yeah, that's a great point. So let's write that down for the notes. I think it's kind of important. There are 2 important questions that I want us to be thinking about. Guys, having a spanning set is a good thing. If you know a set of vectors that spans your vector space, what it really means is that everything in your vector space can be broken down in terms of that spanning set. Isn't that what we just did right here? We broke down every cubic polynomial. Every cubic polynomial has been broken down in terms of these 4 specific building blocks. They are a spanning set for P3 of R. So this is a really important idea. And so that's going to be at the heart of what we're gonna do here. Two important questions. The first one is, given a subspace S of V, find a spanning set for S. I want everybody to be able to do that. And I'm gonna say C warm up number 1. This one right here, because what did we just do in this warm up? We have our subspace S. And we found a spanning set for it, right? Everything in S is a linear combination of these two building blocks, right? We can make everything in S as linear combinations of these two. That's this idea. How do we find a spanning set for S? Okay, can you leave yourself a little bit of space here? I'm gonna give you notes on how to answer this. It's gonna come in 3 steps here in just a moment. I'll come back and fill it in just a moment, but I wanna go on. I wanna get both of my big picture questions down first. The second question is, given a set of vectors, if somebody hands you V1, V2, and ... up to Vn, in some vector space V, if somebody gives you these vectors, decide if they span V in the sense of that definition over there. Right? Decide if they actually span V. So in warm up number 2, the answer would have been no, because the span of these 3 vectors was not M3 of R. It was only the skew symmetric 3x3 matrices. That's not all of them. That's just some of the 3x3 matrices. So in warm up, I'll just add this here. In warm up number 2, the answer was no. The vectors that we were given in that original problem are not a spanning set for V. But in warm up problem number 3, the answer was yes. Because if we take the span of those 4 powers of X over there, we do get the entire P3 of R. So this is kind of a yes or no question. Decide if the vectors span S or not. It's just yes or no. Edgar, do you have a question?
Yeah, so the individual vectors on problem 2, that would be the individual matrices?
Yeah, this would be like V1, V2, and V3. Absolutely, yeah. And same thing over here. This would be V1, V2, V3, and this would be V4 in this case. We have 4 of them. Exactly, yeah. So we can kind of think about that notation. Okay, I'm going to fill in. I'm going to start with the first question first. And by the end of tonight, everybody should be able to address both of these questions. This is the biggest thing I want to get done with tonight. Given a subspace, how do we find a spanning set for S? Well, the first step, there's 3 steps, A, B, C. The first step is to write the general form. Write the general form of a vector in S. And by general form, I mean using variables. So just write the general form. Now, in this first warm-up problem, they already gave that to us. This thing I circled right here is sort of been given. That is the general form of S in warm-up problem number 1. So we try to write what does a general form of one of these vectors look like using whatever variables we need to. Here we use the variables A and B. Okay, so that's the first step. The second step is to bust out the variables that you used in step A. So step B is we bust out those variables. You saw me do that right here. I took this general form and I busted out or factored out the A and the B. And I made it into like an A term and a B term. Now, what you notice by busting out the variables is you expose what the actual vectors are that you're looking for in your spanning set. Right? Guys, these are a spanning set for S. Clear enough? Everything in S can be built as a linear combination of these two. That makes them a spanning set. Right? So that's exactly right. Once we bust out the variables, the third step, step C, is to make a list of the vectors that remain. Make a list of the vectors that remain. And what I mean by that is, okay, so you have this linear combination here with the A times something plus B times something. The vectors that remain are just these guys. Those are the vectors in S that are going to form our spanning set. Is this good enough? I just had a brilliant idea. Happens once every 3 years or so. I want to do an example of this, and I think I can use problem 28 from tonight's homework to do it. So I'm gonna answer one of your homework problems, but also explain this idea as well. And it'll be kind of killing two birds with one stone, as they say. So let me pull out number 28 from tonight's homework. So we're gonna do an example. I would keep this in your notes though, and then just copy it over to your homework later. So this is from section 4.3, number 28. It has to do with null spaces. So let me find it again here and just get the matrix in front of me. So let's let capital A be the matrix 1, 3, -2, 1, and then 3, 10, -4, and 6. And the third row is 2, 5, -6, and -1. The question number 28 asks you to find the null space of this matrix. I'm going to do a little better than that. I am going to find a spanning set for the null space of A. Remember, the null space of A is always a subspace. That was one of the things in the videos, that long video that you watched. A null space is always a subspace, so I could be hoping to find a spanning set for it. Okay, so let's do that. Let's find a spanning set for the null space of A. All right. The way you're going to do this is you're first just going to do what the homework problem is asking, which is you're going to find the null space of A. At that point, you can kind of draw the line on what you need to submit by tonight. But then I'm going to take that null space of A and find a spanning set for it as a sort of an extra add-on at the end of it. Okay, I think this will work pretty well. Let me just remind you guys, because I have had a few people asking me about this. When you're talking about the null space of a matrix, you're really just talking about a system of equations where you build the A sharp. So you're going to start off by so again, I'm kind of taking a quick deviation from talking about spanning sets. What you're doing is you're just augmenting this matrix with zeros. Okay, so for null spaces, it has to be augmented with zeros, nothing else in this far right column. Okay. And to find the null space, you're just solving this system. I could have asked you this problem a month ago. I could have said, find the solutions. And you'd have that augmented matrix. And we learned several weeks ago that we just have to do EROs, get this thing into row echelon form, circle our pivots, introduce free variables, all that good stuff, right? So let's actually just do it here. So I would probably start with A12 of -3. So on this first step, I'm gonna leave the first row alone. In fact, I'm gonna circle that pivot. That 1 is a nice pivot right away. I'm gonna take -3 times the first row and add it to the second row. -3 times the first row, adding it to the second row, and I get 0, 1, 2, 3, augmented with 0. There's another pivot. At the same time, just because I want to be efficient and save a little time here, I'm going to do A13 of -2. So this means I'm going to take -2 times the first row and add it to the bottom row. So I'll have 0, -1. Let's see, -2 times the top row, that's 4 plus -6, which is -2. -2 times -2 times 1 is -2, and I add -1 to that, I get -3 and then 0. Talking real fast, sorry. Now, you might notice that the third row is just the negative of the second row. So what that would mean is that if I do one more step, I would do A23 of 1, but I'm gonna save the time on that. Guys, we have sort of graduated from ERO hell in this class by now. If we want to get a little fast and fancy with it, and not always write out every ERO, not always like go into all the details, I feel pretty good, especially after grading the midterms. I can tell most people are doing pretty well with it at this point. So I can just see that what's going to happen is the third row is going to get wiped out. It's going to become a row of zeros, which, by the way, guys, a row of zeros is basically worthless information. It doesn't tell us anything. So I can cross this off and just focus on rows 1 and 2. Okay, now I have some unknowns here. They didn't give us any unknowns in the problem, but I'm going to introduce them as X, Y, Z, and W like we often do. And the point here is you can see that both Z and W are free. So I will, just as fast as I introduce Z and W, you don't have to change the Z and the W into 2 other letters again. But I think I explained in chapter 2 that I always like to use these same letters for free variables, just so I get in the habit of this. But if we look at the second row here, y plus 2z plus 3w is equal to 0. So now I solve for y. So I just plug in z equals r, w equals t, and I move it to the other side of the equation. It should be -2r minus 3t. That would be for y. Okay? Agree with me? This is really a chapter 2 problem. Okay? You can see everything we're doing right now, we did several weeks ago. The last thing we need to do is figure out what x is. And that comes from the top row. So x, I'll write it here, guys, if that's okay. X plus 3y minus 2z plus w, that should equal 0. And now if I want to solve that for x, I have to move everything else to the other side of the equation. So I would have x equals -3 times y, but I'm going to replace what y is. Y is -2r minus 3t. Then I have to add 2z, which means I'm adding 2r. And then I have to subtract w, which means I'm subtracting t. And I should clean this up a little bit. So this is going to be 6r plus 2r. I'm going to come up here, guys. X is actually 8r. And then I have a -3 times -3t. That's 9t minus t. That's plus 8t. With me? So what is your null space of A? What is the answer to this homework problem? Well, we know how to write this thing as a set. I'm going to actually do, the one thing I am going to do that I don't think is, that I've done that often, I'm going to actually represent the 4 slots as a vertical column rather than as a row. It turns out it doesn't matter. It doesn't really matter, but I'm going to write it vertically. So I'll have 8r plus 8t, that's the x solution. The y solution is -2r minus 3t. The z solution is r, and the w solution is t. So I just make this vector, and then I do the usual thing with the colon here, such that r and t belong to the real numbers. And so if you're trying to get the homework problem down, that would be the answer. That's as far as you need to go for the homework. And as you can see, 90% of what is on that board is stuff that you've been doing for weeks, right? It's actually not really a new thing. It's just the word, a null space that we've just recently learned about. But when I say null space, all I mean is augment your matrix with a column of zeros and just do the chapter 2 process, the Gaussian elimination. Does that make sense? Now, this is a subspace. By the way, this is a subspace of what? This is a good question. A subspace of what is the big universe that we're working with here? Rn is exactly right. From the video, I mentioned that the null space of a matrix, if A is M by N, the null space is a subspace of Rn. What is N on this problem? It's 4. You can just see this is a 3 by 4 matrix. M is 3, N is 4. Exactly right. So you notice also, just in case, if let's say you didn't remember that, you can just look at this and say, well, how many slots are there? There's 4 slots. So that means that you're talking about a universe of R4. It is a subspace of R4. Okay. So now I want to get to the new part of this material, which is, what if we want to find a spanning set for that? So a spanning set for that would be sort of a follow-up. You don't have to do this part for the homework unless you want to. You can if you want, it doesn't hurt. But how do we find a spanning set? So what does it say over here? It first says, write the general form of a vector in S. Well, using variables. That's actually what this is. That's what all of this work has been. This is what so this is already step 1. Or step A, I'm sorry. I called it A over there. So step A would be to write that down. Right? Now I'm going to go on to step B. Step B says bust out the variables. And here I see that I have 2 variables in my notation, which are R and T. I'm going to bust them out, meaning I'm going to factor them out. Okay, so watch me how I do this. Okay, the way I'm going to do this is I'm going to say null space A equals, I'm going to go ahead and use my big brace again, but I'm going to bust out the variables. I do that one at a time. So I have 2 variables. I'm first going to bust out the R. Okay, so don't let me go too fast on this. This is something that will become second nature for you, I'm quite sure. But at least when you're first seeing it, it might take a minute to figure out what I'm really doing. When I say bust out the variables, I just mean factor out the variables. So I look here, here's the R factored out. So where do I have R's in here? Well, there's an 8 with the first R, so I'm going to put that there, right? And then there's a -2 with the second R, I put that one there. Then there's 1 R, and then the bottom slot doesn't have any R's in it at all, so I'll put a 0 there, okay? And then I'm going to go plus T times, I'm going to do the same thing. I'm going to take, what are the coefficients of the T? I have an 8 again on the first slot, then I have a -3, then I have a 0, and then I have a 1. Okay, so this is just busting out the variables. That is step B of my process. Okay. And then step C, last step, just says make a list of the vectors that you obtained, the vectors that remain. So what is my spanning set? I'm ready to write down the answer, guys. I don't even have to do any more work, really. The spanning set here is equal to, and again, it is a set, so I'm going to use braces to emphasize that. But what we do is we just list the vectors. So one thing that's important here, guys, is you get rid of the R and you get rid of the T. You don't write those down again. You just list these vectors, 8, -2, 1, 0, comma. The second vector is 8, -3, 0, 1. And that is your spanning set. That is your spanning set for E3, sorry, for the null space of the matrix. That is a spanning set. So a spanning set is a set of vectors whose span would be your subspace. Is that clear enough? Any questions there? Yeah. Okay, you can talk to me about it later. I want to do one more example of this before we go on to question 2. want to do one more example. Let's do this one. This one's not from the homework. This is just I'm making this up. Let's let B be equal to P3 of R. So I'm gonna, you see why we have to do so many of these? Right here, we're working in the universe of R4. Now I want to give you what it would look like in some other universe. So let's take P3 of R, and I'm gonna let S be the set of P of X belonging to P3 of R. So it's those polynomials such that P of 5 is equal to 0. Now, I'm gonna ask you to take my word for it that this really is a subspace. We can't find a spanning set for something that's not a subspace, so it has to be a subspace. Over here, this was automatic because null spaces are always subspaces. We knew that from my notes. Here, I'm giving you something kind of out of the blue. This S is just kind of out of the blue. I'm just asking you to trust me. I wouldn't lie to you guys, that this is a subspace of P3 of R. And what I want to do is find a spanning set for S. And just to be very clear with this, S is not all cubic polynomials. S is only those cubic polynomials that when you plug in 5 for X, you get 0. Right? So like an example would be X cubed minus 125. You plug in 5 for X, 5 cubed minus 125, that would be 0. So there are some polynomials in S, but it's not everything. It's not everything. So let's go through the 3-step process here, guys. Let's start with step A. Step A, by the way, is usually the hardest part. So I'm going to do step A. What we need to do is we need to write down the form. What's it say? Write the general form of a vector in S. Now, this is a common mistake that I see people do. Okay, so polynomial, we're going to write it as P of X this time. And what I'll see people do is they'll say, oh, okay, I'm going to write the general form as ax cubed plus bx squared plus cx plus d. And actually, that would be the general form of a polynomial in V. Right? Something from the big universe could look like this. This, if I write this down, I am nowhere incorporating the fact that P of 5 is 0. So you know what I want to do right now? I actually want to plug in 5 for X and set it equal to 0 and see what it tells me. So if I do that, I'm going to need more room. I'll just get started here. P of 5 is 125A plus 25B plus 5C plus D. And I'm going to set that equal to 0, my friends. Come back over here. Set that one equal to 0 like that. And actually, you have an equation there that could be thought of as just a 1-row matrix, right? 125, let's just write this as a little matrix here. 125, 25, 5, 1, augmented with 0. That's like our system, and our unknowns here that are going with those variables or with those numbers are A, B, C, and D. Okay. Guys, A, B, C, and D cannot just be anything. They have to be set up in such a way that P of 5 will equal 0. This condition is reflected by that matrix. That matrix is going to force us to choose A, B, C, and D so that they do satisfy this equation over here, you see? And of course, I'm gonna cheat big time and call this a pivot. Okay, I'm supposed to divide by 125 there, but that's basically a pivot. The point here, guys, is that B, C, and D are all free. These are all free. The only thing that's not free is A, right? A is not free, but I could solve for A in terms of B, C, and D. So let's see, how is that going to work? One. Let me just see if I can do it in my head. I'm taking that equation over there, the bottom right equation, I'm solving it for A. So I'm gonna get negative 25B minus 5C minus D. I'm gonna divide all of it by 125. And if I want to make that a little nicer, I'll just go ahead and simplify this. 25 over 125, that's 1/5. So negative 1/5 of B minus 1 over 25 of C minus 1 over 125 of D. That would be the A value. And guys, I am still on step A. I am still trying to get the form of P of X. This is the hardest part of the problem, is just getting this form. But I'm ready to write it down now. I am ready to write it down. What is the form of a polynomial in S? Well, it's ax cubed, but with this A, negative 1/5 B minus 1 over 25 C minus 1 over 125 D, all of that with an x cubed plus bx squared plus cx plus d. That is the form. That is the form. Okay. Yeah, I think that looks good. That looks exactly how we should have it. Okay. So with that in mind, I'm done with step A. This is the, so don't be too fast here. This very first line is not the form. Unless I was trying to find a spanning set for P3 of R. If I wanted a spanning set for P3 of R, I would bust out the variables here and just get x cubed, x squared, x, and 1, which was our warm-up problem a few minutes ago. But here I want a spanning set for something slightly more complicated than P3 of R. It's those polynomials with this extra catch, this extra condition, which is that when I plug in 5 for x, I should get 0. And if I want those polynomials, it's got to be this one. All right, let's go to step B. Step B. What does step B say? Bust out the variables. So I'm going to take my P of X now, guys, and I'm going to bust out the variables. Keep in mind here, the variables are B, C, and D. They are not X. They are B, C, and D. So I'm going to bust out the B. When I bust out B, I get negative 1/5 of x cubed plus x squared. Everywhere I see a B. So guys, there's a B here and a B here. When I factor that B out, I have a negative 1/5 times x cubed plus x squared. All right. Then let's bust out the C and do the same thing. When I bust out the C, I get negative 1 over 25 plus x. Is that right? No, I'm sorry, negative 1 over 25 x cubed plus x. There we go. Okay. So you see negative 1 over 25 is also multiplied by x cubed here, right? And then finally I have to bust out the D. When I bust out the D, I get negative 1 over 125 x cubed plus 1. Everybody see how I'm doing that? Looking everywhere, scanning my form of my polynomial, I'm pulling out the variables, the B, busting them out, B, C, and D. There's 3 of them. Because there are 3 variables to bust out, I get 3 polynomials here. And so now for step C, which is where we write down our final answer, we're just going to make a list of the vectors that remain. So my spanning set, we're going to go ahead and go straight to the answer now, guys. The spanning set, we're going to write it with braces. And we're going to list them out. Negative 1/5 x cubed plus x squared, comma. So we're using commas here, right? And then the next one is negative 1 over 25 x cubed plus x, comma. This is a list with commas to separate. The last one is negative 1 over 125 x cubed plus 1. If you plug x equals 5 into any one of these, you will get 0. That was part of the whole point of this, is that our subspace S is supposed to be, we're supposed to be looking at polynomials that when you plug in 5, the output is 0. So a good way to check your answers is to just try it. Plug in x equals 5 into any one of these, you better get 0. Does this make some sense? You know, the other thing, I'm not surprised by this answer. Because how many vectors did it take to span P3 of R? P3 of R? 1 x squared, and x cubed. I needed 4 building blocks to be able to span P3 of R. Well, now S is not all of P3 of R. S is a smaller set inside of P3 of R because we have this constraint here. We're not looking at all polynomials anymore. We're only looking at some of them. The ones where when we plug in 5, we get 0. In other words, S is smaller than V. I'm not surprised, therefore, that my spanning set has less vectors in it, right? I needed 4 vectors to span V, to form a spanning set for V, but I only needed 3 here for S. Not surprising, not surprising at all. Somehow the size of a vector space, this is something we're going to be talking about. And it is related to sort of how many vectors you need to be able to span it. But we'll come back to this concept on Thursday, but at least for now, it's kind of some reasonable intuition. How do people feel about question number 1 here? Feel okay with that? You have the problem on the homework for tonight. You remember the one, I think it's number 12, the 2x2 matrices where the 4 corners have to add up to 0. Right? We could find a spanning set for that too, right? We could just say, what would it look like? Actually, you know what? Okay, I was gonna take a break. Before I take a break, I want to just talk about that while it's on my mind. And then we'll take a short break. You know, so this is another example. Find a spanning set for S, which is the set of A element of M2 of R. So we're going to take matrices that are 2x2. M2 of R is the 2x2 matrices, such that the 4 entries of A sum to 0. I just want to do this one real quick. I think for your homework for tonight, you have to show that that's a subspace. So you're going to check that it's closed under addition and scalar multiplication. That's not quite the same thing as what I'm going to do right now. I want to just find a spanning set for this. So let me go through step 1 here, or step A, sorry. I call these A, B, and C. Step A. Step A, and this is the most important part, write the general form of a vector in S using variables. Okay? So, and the 4 entries are supposed to add up to 0. So I'd like to know what you think about this proposal. I'm going to just write it down. What about something like this? Would that work? If you add up those 4 numbers, you definitely get 0, right? But is it the most general form that we could have? I mean, I don't think so. Couldn't I have like 6, 7, 8, and -21? Those 4 numbers add up to 0, but they don't fit this pattern, right? They don't fit the pattern that the second row is just like the negative of the first row. So actually, this is the reason I wanted to show you this, is you really need this form to be as general as possible, right? This is, if the question had said 2x2 matrices where each column adds up to 0, then I'd be totally on board with this. If it said column by column, I want them to add up to 0, then I'm totally with you. But this one just says all 4 entries, just going all the way around, they add up to 0. So let's try again. Actually, I'm gonna be quiet for 30 seconds. See if you can write down what would be a good answer for the general form of a 2x2 matrix where the 4 entries all add up to 0. Just think about how you would do it using variables. I'll give you 30 seconds. I sometimes like to pretend like somebody gave me an assignment. Write down a 2x2 matrix whose 4 entries add up to 0. And you know what I can do? I can just make the first 3 numbers whatever I want, as long as the last one cancels them all out. That's what I did with my 6, 7, 8 example a minute ago. I said 6, 7, 8, and then the last one just had to cancel them out. Does anybody want to try what they have here? Do you have an idea? Start here with A. All right. B, C. That's it. That's exactly right. That's exactly right. The first 3 numbers can be anything you want. So just make letters for those. A, B, and C. As long as the last one cancels it out, you're fine. Now, somebody might say, well, wait a minute, would it have been okay to go like A, B, C, and then negative A plus B plus C? This is also correct. This would be another correct answer. There's not just one spanning set for a vector space or for a subspace. So there might be lots of right answers. But yeah, we would be perfectly good doing this. Okay? Everybody follow that? 6, 7, 8, and then I got to make the rest of it. The last slot has to cancel them all out. Negative 21. Right. So that's the kind of idea here. Now, what I'm going to want to do for step B, I think we're getting pretty good at this now. I'm going to bust out the variables right now. I bust out the A. When I bust out the A, and then I look at, well, what's left over? Like, where are all of the A's? There's one A in the upper left corner, nothing going in the top right or in the lower left. But then the A in the bottom right corner does have a minus in front of it. So I'll put -1 on that. Okay, and then we keep going. Plus B times, and now I'm going to go to the B variable. There's nothing in the upper left corner. There's one B in the upper right, nothing in the lower left, and -1 of those in the lower right. Okay, and then finally C. So we add C times nothing going on the top row at all. And then in the bottom row, I have a 1 and a -1. Okay, and so that's step B. And then finally, our final answer here, guys, and then we'll take a little break. Step C is where we just make a list of, I'm going to put this in braces here. We're just going to make a list of the matrices themselves without the A, B, and C. So 1, 0, 0, -1, comma. Second one would be 0, 1, and 0, -1, comma. And the third one would be 0, 0, 1, -1 on the second one. Just like so. That's it. So it took 3 matrices to span M2 of R. So if any of you want to get smart with me on the homework, this is the homework problem actually asks you to prove that this is a subspace. So that would mean you would need to show that it's closed under addition and closed under scalar multiplication. If you want to get fancy though, you could do that. I'll let you do that. I'll try to remember to tell my grader to accept it. You know the fast way now to show that S is a subspace of M2 of R, avoiding the closure under addition and scalar multiplication? It's the span of these guys. Exactly. So S is just equal to the span, right? Remember, anytime you take the span of anything, it's automatically a subspace. So that's a sort of a backdoor approach to showing that you have a subspace. Express it as a span. And of course, that means you need to find the spanning set. And we've already done that right here in blue. Okay, so you could do that if you wanted to. I'll let you get away with that. Any questions here? Okay, thank you guys for your attention. Let's take a break for about 10 minutes and then I'm gonna address this second question here that we haven't talked about so much yet. But we'll do that when we come back. Favorite thing? I'm gonna run down to my office because I forgot to bring some exams up here. Would you erase for me this board and this board, just not the one on the. Okay, thank you so much. I really appreciate it. I'll run downstairs and grab my stuff I need. Anybody's got any more homework questions? You can throw them on the board there as well during this 10 minutes.
Did he show on that? Okay. Did he show on? Okay. Yeah, I was walking one too. Some of us also like not to the first basic to the first basics. So now I. There's no one that with the kid can do. The one that's like. Figure something out. It's been a long time.
Nice to see you. Thank you, Anthony. Joanna? Right. You weren't seated, were you? No. Okay. Is Andy Vu here? Oh, there he is. And David Lamb? Oh. I think he's the best professor for this. He's good at like his whole thing. His problems. I think he's yeah, that's where it's in. Gary? I wish that we had. Yeah. And they have a bit Michael. See,
I got back in yeah, much like I mean, strong this kind of semester.
I got left semester.
Yeah.
Getting busy.
Like, I'm at 97, 87, 86, 81. I'm like, okay, whatever.
This is for 6 lessons. My professor, he was her first semester ever teaching us.
Oh, yeah, are you like approximating?
So she had a class like impossible. They're doing
Yeah.
line.
Yes. All right, like, he was doing the first thing. That's when he made like.
Like the homework, like,
Shit like that, bro. It's like,
oh, yeah. Yeah.
But this over was a hard thing. 50% was like,
It was still a fucking.
it's like some little guys. Like, he used to give us shit ton of homework.
You can't tell people that you already know that. When they teach them lectures.
But he just. Like, bro, this is. It's just like force, never like, don't make any like positive systems. You know. He's smart, he knows his help. What are we gonna do? We can explain like. I feel like that's like. Really smart, but you're gonna like deliver. Really, exactly. But it's like, I wanna know what that is. It's massive tension. It's not your wrong homework assignment. It's not. Okay. They're not your tips for winning a golf tournament. Would that be nice? That would be.
She is.
All right, everybody, I think most folks have made their way back over here. A couple empty seats tonight. Remember, I suggested if you want to go to that SI session that's right when this class meets, you're always welcome to consider doing that, and you can come to my 6 o'clock class instead, same exact material again. And I know that there's at least 2 or 3 students who took me up on that. So, yeah, just if you feel like it would be helpful, I just want to remind you that you're welcome to do that. Whoops, I didn't mean to turn that on yet. Screen. Maybe it'll go away at some point. Yeah, so I wanted to spend a few minutes. I see there's another problem on the sideboard over there, and I'm glad, I don't know who wrote it up there, but I'm glad you did. That's a good one to maybe talk about together. So I'll save a little time. Last 5 minutes or so, we'll take a look at number 6 from 4.2. But I want to address this second question down here. This is also very important, guys. If I give you a set of vectors, right? So you don't have any mystery about it. I give the vectors to you. I can ask you, would they be able to span V? Okay. And so here's a warm-up problem. We're going to experiment with this by just doing a warm-up problem. Here's 3 vectors. You can see that each of them has 3 slots. So you know what universe that is. Vectors with 3 slots, that's R3, right? So the question is just, do these 3 vectors form a spanning set for R3? Now, again, what does that mean? That would mean that any vector whatsoever in R3 can be made up as a linear combination of these 3. Okay, so I'm going to start solving. We're going to go right into the solution here. And what I'm going to do, guys, is I'm going to take linear combinations of these vectors. 2, -1, 4. So A times the first vector plus B times the second vector plus C times the third vector. I'm going to set that equal to. So I'm taking a linear combination of the 3 vectors that I gave you, and I'm just going to try to set that equal to some random x, y, z. And the question is, for every x, y, z, would I always be able to find A, B, and C? Right, so if I give you any point of R3, can I express it as a linear combination? Because actually, all of these linear combinations, that is what the span of these vectors is. So the question is that going to be all of R3? Is every vector in R3 going to be expressible that way? So I'm imagining this is a fixed vector. And I'm asking the question, can I solve for A, B, and C? I didn't say I want to actually solve it. I just said, thumbs up or thumbs down, yes or no, can I solve for A, B, and C? Right, so let's write that down. Can we solve this? Can we solve this for A, B, C, regardless of what X, Y, and Z are? That's really the $1 million question here. That's the question. If I give you X, Y, and Z, would you always be able to solve for A, B, and C? If the answer is yes, then this answer is yes. They are a spanning set. They do span V. If the answer here is no, then the answer over here is no. That's kind of how it works. Now, this equation here, I'll box it up for us here. This equation, it looks like one equation, but it's actually 3 equations. Because there's a left slot going all the way across, and there's a middle slot going all the way across, and then there's a right slot going all the way across. Let's just write down what those slots, what those individual equations would be. I'm gonna do left, middle, and right. I'm gonna make an equation for each of those slots. Now, if I go across the left slot, so I'm gonna kind of underline the left slot, 2A, right? And then plus 3B, and then plus C. And then on the right-hand side, the left slot is an X. Okay? Now, if I go across the middle slot, if I take the middle of everything, negative A minus 3B plus C equals Y. And then if I do the right slot, we'll get another equation, which is 4A plus 5B plus 3C, and this one would be equal to Z. So just kind of match things up on the left side and the right side of the equal sign. And so this is what I mean, that this one equation in the box is really 3 equations. And of course, this can be put into an augmented matrix, as we've seen many times, right? I can write this now, 2, 3, 1, augmented with X, -1, -3, 1, augmented with Y. And the third one would be 4, 5, and 3, augmented with Z. And the unknowns in this particular setup are going to be the A, B, and C. The unknowns are A, B, and C. Now, the question is really, can we solve this? In other words, is it consistent? That's the question. Is this consistent? Well, we've answered questions like this before. If I give you a system of equations and I ask you, is it consistent? Well, I have to do my EROs on it. Right? I have to bring it into row echelon form. Let's just do this real quick. I'm going to do this fairly quickly. I'm going to permute the first 2 rows, so P1, 2. So then I get -1, -3, 1, and Y. And then the second row is 2, 3, 1, and X. And the bottom row is just staying the same for the moment, 4, 5, 3, and Z, like that. And now I'm going to use this -1. I'm going to take multiples of the first row and zero out the entries below that -1. So I'm going to do A1, 2 of 2. So the first row I'm leaving the same. But I'm going to take 2 times the first row and add it to the second row. So 2 times the first row added to the second row should give me 0, -3, 3. And now we got to be a little careful on the right-hand side. 2 times the top entry added to the second row, that's X plus 2Y, if I do that carefully. Right? And then at the same time, guys, I'm going to do A1, 3 of 4. That means I'm going to take 4 times the first row and add it to the bottom row. I'm going to get 0, -7, 7, and what is it, 4Y plus Z over here in the bottom right corner. Okay, now what I'm going to do is I can see the -3 and 3 and the -7 and 7. They're kind of like multiples of each other. Let's actually try to zero out these 2 7s down here. I'm going to do A2, 3. Forgive me for fractions for just a minute. I'm going to do some fractions here. I'm going to take, what is it, -7/3 times the second row and add it to the third row. Okay, so ready to go? Here we go. -1, -3, 1, augmented with Y. Second row, I'm leaving that the same, 0, -3, 3, and X plus 2Y. And the bottom row is going to be 0, 0, 0. So if I take -7/3 times the second row and add it to the bottom row, I'm going to put a little star here for a minute. What is star going to be? I need a little room here. -7/3 times X plus 2Y added to the bottom row, which was 4Y plus Z. That would actually be what goes right in there. Okay. Now, guys, I am ready to, I've done all the grunge work. Now I got to actually circle my pivots. Here will be a pivot right here. Technically, a pivot needs to be a 1, but I don't care too much about that anymore. I just want to know where is the position of the pivot. Here's a -3, that's going to be a pivot. Okay, and what about in the bottom row? 0, 0, 0, where's the pivot? Is this a pivot? Oh. It's this whole thing here, right? That's what's technically where that star is. It's a pivot unless it's 0. Well, I bet I could put some numbers here that would, what if I just let Z equal 1 and everything else is 0? That would be a pivot, would it not? If I get a pivot in the far right column, is my system consistent then? No, it's not. In fact, how many solutions do we have? 0. Can we solve for A, B, and C regardless of X, Y, and Z? No, right? This is bad, 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 right? It's been bad since chapter 2. Getting pivots in the far right column just means no solutions to the system, right? So this is inconsistent. And so the answer therefore is no. This was a yes, no question. Is it a spanning set? But are these 3 vectors a spanning set for R3? The answer now is quite clearly no. Okay. Now, I want to make a few comments about this. The first one is these 3 original vectors here. Do you see them showing up anywhere later in the work that we did on this middle board? Look at these 3 vectors. Do you see them anywhere over here? Anthony, you're shaking your head. Where are they? They're in this matrix. How? Say again? As columns, right? As columns, exactly. 2, -1, 4 is right there. 3, -3, 5 is right there. And 1, 1, 3 is right there. You know what, guys? That will always happen. When you set up this question to answer this second topic here that we're talking about, the original vectors that were given to you are going to get laid out column-wise in your matrix. And what that means, my friends, is that you don't really need to do any of this ever again. Because you can just jump to here. You can say, oh, I'm going to put the first vector into the first column, the second vector into the second column, the third vector into the third column, and then my unknowns go into the last column. Okay, so I'm saving you work right now. I did it once just to show you how it's playing out. But what you're going to realize is every one of these problems, that same thing would happen. So feel free to skip this part that I just kind of put a big, let's just put a big red X through it. We don't need to do all of this anymore. We can go straight to the matrix. The running joke of Math 250B is that the answer to everything in this class is put it in a matrix. All right, that's exactly what we did. Okay. Another thing I want to comment on. We started with XYZ here, which of course that makes sense. You're putting an arbitrary, sort of a random vector from R3 into that far right column. Now, as you do EROs, you notice the X, Y, and Z, they kind of get jumbled up. They get kind of torqued around into different expressions. But what you really end up with over in this far right column all the time, guys, is just some sort of an alphabet soup of X's, Y's, and Z's, right? It's not the original X, Y, Z in this order. You can see over here, it kind of got all tangled up. In fact, this is pretty messy at the end of the day. But you know what? Do we really care that this is a Y and this is an X plus 2? We don't really care what those expressions are. Just that as long as they're not 0, they would be pivots. So you know what? It doesn't even matter. It doesn't even matter. You don't need to do this on this example, but I'm going to, so don't change your notes. But here's how we're going to do the next example. I am just going to do this. I'm just going to put some hashtag symbols there. And I'm going to say, yeah, when I do an ERO, those hashtags will change to something else, but I don't care what they are. I don't actually care. The point being that at the end of the day, what you will have over here is just some mishmash of X's, Y's, and Z's in some expressions. And the point is, if I see 000 hashtag, I'm going to know to put a pivot around that. This saves you an immense amount of aggravating algebra, for example. Nobody wants to sit here and like clean this expression up. Turns out we don't have to. It's not important. The point is that as long as these hashtags are not zero, then you would have a pivot there, yeah? And that's actually all that matters. You would have a pivot there, and so the answer would be no, it's inconsistent. So all we care about is yes or no on this, guys. Is it consistent or not? That's the only thing that matters, and that comes down to whether there's a pivot in the far right column of your matrix or not. Okay, so pretty nice, pretty nice. The other thing I wanted to point out is this coefficient matrix happens to be a square size, 3 by 3. We would be able to decide whether this is a consistent system or not, since after all, the original vectors are just in the columns here. We could, what can we do? What's a powerful thing that we learned how to do with a square matrix in this class? The determinant. The determinant allows me to decide if the matrix is invertible, right? If the matrix is invertible, well, then you would be able to solve the system. You'd have pivots going all the way down the diagonal and they would not drift into the far right column. But look at this matrix. This matrix is not invertible. We did some EROs and got a row of zeros out of it, right? That matrix is going to have a determinant of 0. So this is actually a general principle that works every time, and I want to write it down for you before I do another example. A general principle that is well worth recording is that given vectors v1, v2, and ... up to vn in Rn. So if I give you 3 vectors in R3, or 5 vectors in R5, or 8 vectors in R8, it has to be a compatible number of vectors. Then these vectors, this set, v1, v2, and ... up to vn, spans Rn if and only if, I'm going to give you a really nice little principle here. And the principle is just that if you take the determinant of the matrix, where I'm going to put the vectors into the columns, which is what we just observed, right? So v1 goes in the first column. These vertical bars are just my way of sort of separating the columns out. So we lay out our vectors column-wise. By the way, that's something new tonight. We haven't done that in the first 6 weeks of the semester. Usually we're writing our matrices, we're filling them out row-wise, right? That's how we used to do everything. Here, we're seeing something a little different. The vectors are getting laid out into columns here, right? And as long as this determinant is not 0. Okay. For the problem that we just worked on right here, the determinant is 0. You can do it with this. Just take this and do the arrow method if you want to. 3 by 3 arrow method, you'll get 0. I promise you. You'll get 0 for that determinant. And if you get 0, that's bad. That's bad. If you get determinant equals 0, then the answer here is no. The vectors do not span your vector space. That's bad. That's what you don't want. Does this make sense? Well, let's do another example. Let's do another example. So here's another one to practice on. I'm going to do this one the fast one. I've kind of given you, we've made some observations that I hope will make this go quickly for us, right? That's going to be the idea. So on this example, I'm going to say, is the set 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4 a spanning set for R3? This camera a little closer here. Sorry. Let's try this one. By the way, this time I gave you the wrong number of vectors, R3, but I gave you 4 vectors. So we're not going to be able to use the general principle. I just told you this principle, and now I'm going to give you a problem where we can't use it. Because to use it for R3, it would have to be 3 vectors. But I gave you 4 vectors. No matter, I'm going to solve this problem in maybe only 1 minute. Okay, because what are we gonna do? We're gonna take advantage of all of the shortcuts that we just talked about in that last example. We're gonna go straight to the matrix. We're gonna lay the vectors in the columns. First one is 1, 1, 1. Second one is gonna be 2, 2, 2. The third one is gonna be 3, 3, 3. Fourth one is gonna be 4, 4, 4. And we would augment that normally with XYZ, but I'm going to augment it with number symbol, number symbol, number symbol. Pound signs, I guess is what they're called. And I'm gonna hit this one with EROs, guys. I'm gonna hit this one with EROs. 1, 2, 3, 4 with a number symbol. And I'm gonna take the negative of the first row and add it to the second row, but watch this. Watch this. When I take the negative of the first row and add it to the second row, I get 0, 0, 0, 0. And be careful, number symbol minus number symbol is still number symbol. It's just, because remember, this is really an X and a Y. So when you actually subtract the first row from the second row, you get like Y minus X. It's just some other expression involving the unknowns that you have populated into this last column. So the point is, I guess the point I'm trying to make here, guys, and I didn't realize this till I'd been teaching this class for 10 years, is you don't have to keep track of the far right column. You can just keep turning off your brain and just like keep writing number symbols down. Same thing in the third row. These are all going to be zeros and that's going to be a number symbol. When I circle my pivots, number symbol has to count as a pivot. It is not a 0. And so what's the answer to this question? Yes or no? It's no. It's no. It's exactly no, because it's inconsistent. Remember, we're only asking, can we solve the system? We're not actually solving the system. That's the nice thing. If we actually needed to solve the system, then we really would need to leave the XYZ here and actually play nice with that far right column. But because we're just trying to figure out if there's gonna be a pivot over there, we can kind of streamline this process. I just love this. This isn't in the book, by the way.
Oh, nice.
This thing with the number symbols, even though I wrote the book. At some point, I'll put it in there. I didn't realize this for a long time. Was there a hand up?
Yeah.
Yeah, Andrew?
Can you say like the span of 1, 1, 1, so they're all like in combinations of each other and 1, 1, 1 doesn't have to grow.
This is exactly, this is a lousy set of vectors, guys, if you're trying to span something. Because you got 1, 1, 1, which goes like that. And 2, 2, 2 is just that. 3, 3, 3 is that. And 4, 4, 4 is that. What are you gonna get when you take linear combinations of a bunch of vectors that are all pointing in the same direction? You're just gonna get stuck on that line, right? You're not gonna be able to find points that are anywhere off of the line. So yeah, this is not a good set of vectors at all. Even though I gave you 4 of them, seems like that ought to be more than enough. But it turns out it's not. It's not at all. Okay, good point. Let's do one more and then we'll go to that homework question. This is just about wrapping up this section. Feeling pretty good here. Oh, by the way, could we have used the determinant here? Careful. What's the size of the matrix? 3 by 4. So can we use a determinant on something like that? Heck no, right? It's got to be a square size. So this whole general principle thing, it's actually pretty easy to remember when you can use the general principle. It's just whenever the matrix is a square size, the coefficient matrix. So you don't have to memorize that too difficult. It's pretty straightforward. And guys, remember, good goes with good, right? An invertible matrix is a good thing, and being able to span your vector space is a good thing, right? So these are absolutely compatible with each other. Okay, I'm gonna do one more that's not just R3. And then I think we're gonna be really in good shape for this. Okay? So is the set 1, 2 plus 3x, 4 plus 5x plus 6x squared, 7 plus 8x plus 9x squared plus x cubed. That set right there, my friends, those 4 polynomials. Is that a spanning set for P3 of R? So we're in a different universe this time. This time the universe is P3 of R. And notice I have four things here. 1 and then 2 plus 3x, 4 plus 5x plus 6x squared, and the last one over here. So I'm gonna do this one quickly by following the guidance of those last two examples. We're gonna go straight to the matrix. Now, when I go straight to the matrix here, guys, we do need to be a little careful. We're not literally going to write polynomials into the matrix. Right? What we actually are going to be writing down in the matrix itself will just be these coefficients. So like the first one is a 1, and I can lay that out as a 1 with a bunch of zeros. This is really 1 plus nothing times x plus nothing times x squared plus nothing times x cubed. So I'm just laying that in the first column. The second column is 2 plus 3x plus nothing x squared plus nothing x cubed. The third one would be 4 plus 5x plus 6x squared, and then there's no x cubed. And the last one, we have a 7, 8, 9, and a 1. We're doing this column-wise, right? And that's it. And then we augment this with my good old pound signs, number signs. All right. I'm not even going to do any EROs. There's your pivots. That's where they're going to be, right? No need to do any work here. Do we get a pivot in the far right column? Not at all, right? We don't. In fact, because there's no pivot in the far right column, is that good or bad? That's good. That means this is consistent. The answer to this question is going to be yes. It's going to be yes this time. Okay, pretty nice. Pretty nice. Okay. Questions about this? This is kind of how we address question number 2 here. I promised by the end of the night I would have good answers to these first 2 questions over here, and I think I've pretty well done it for you now. Everybody with me? Okay. And again, by the way, you could have, on this one, you could have used a determinant as well. It's a 4x4 matrix. So anytime it's a square matrix and you have a determinant that makes sense, you can calculate it and use that. If you don't want to like actually do EROs, this one's easy to just circle the pivots. But if it was a 4x4 matrix that you wanted to do the determinant for, that would be fine. That would be fine. Okay, guys, with the whatever little time I have left tonight, I want to do number 6 from the homework that's due tonight for you, because I think a lot of people probably have had a little issue with this one. So we're going to do it real fast, and then after that, we'll be done. Okay, if everybody's good, no questions on this section. There's actually a handout in Canvas about standing sets. I'll probably send you an email in case you need more practice on it. I've done that for you, but let's take a break from that and just spend the last couple minutes here looking at number 6. What this is S is the set of solutions to, and then they give you a differential equation, y prime plus 3y equals 6x cubed plus 5. And they're just going to ask you, is this closed under addition and scalar multiplication? Okay. By the way, you don't have to solve the differential equation. You could if you wanted to, because it's a first order linear differential equation. So we've learned how to do that using integrating factors back in the very beginning of the semester. But that's not what this is about. They're not actually asking you to solve the equation. They just want to know, is it closed under addition and scalar multiplication? So let me show you how you would write this one up. Okay, I'm just going to do this one for you. We're working in a world of calculus. We haven't done that all night tonight. So we've got to get our minds thinking about calculus functions. The vectors are functions, functions that solve the differential equation. So I'm going to grab 2 functions. I'm going to call them y1 and y2. I'm going to let y1 and y2 be in S. Okay. By the way, I'm skipping over the 0 vector check because I think the question's asking you about closure under addition and scalar multiplication. So we'll just ignore the 0 vector check for the moment and just start with this. Okay. What does this mean? This means that if I take y1 prime and I add 3y1 to it, I get 6x cubed plus 5. And it also means that if I take y2 prime plus 3y2, I also get 6x cubed plus 5. Both of those things are true if we assume that y1 and y2 are solutions to the equation. The question is, what about addition? Y1 plus y2. If I take y1 plus y2 and I stick it into my differential equation here, so I take a derivative and then I do 3 times y1 plus y2. The question is that a solution still? Is this still equal to 6x cubed plus 5? I sure don't think so. If you actually FOIL this out, if you distribute the derivative and distribute the 3, you can rewrite this, guys, as y1 prime plus 3y1 plus y2 prime plus 3y2. Right? You can break this up into the y1 parts and the y2 parts. And y1 prime plus 3y1, what's that equal to? 6x cubed plus 5, right? And y2 prime plus 3y2, what's that equal to? 6x cubed plus 5. And my friends, that does not add up. That does not add up to 6x cubed plus 5. It adds up to 12x cubed plus 10, actually. It adds up to something that's the wrong thing. So the answer is no. y1 plus y2 is not in S. It fails to be closed under addition. And normally we would be done now. If it fails to be closed under addition, it's game over. However, I think the instructions here are asking you about the scalar multiplication as well. So we should technically do that also. Do I have even a minute left? Not really. Can I, do you want me to do it for one more minute?
Yeah.
All you gotta do real quick, so just let K be an R. And y1 as above. Just do that. You don't have to rewrite the whole thing out again, just say y1 as above. And all I'm gonna do is plug in K times y1. So let's do it. K times y1 prime plus 3 times K times y1. All I'm asking you is, does that equal 6x cubed plus 5? Because that's the $1 million question for being an element of S. And you can see right away that it's not, because you can pull the K out of everything. You can pull the K out of absolutely everything, factor it completely out, and then what you get is K times 6x cubed plus 5, which is not the same thing. That is not the same thing as 6x cubed plus 5, unless K equals 1. But it has to be for every value of K, and it's not. So this is also fails. Also fails, so this is a no-go. K times y1 is not in S, just all that jazz can just be written down, and you don't have a closure under either of the operations. So this is not a subspace. It's not a subspace. Guys, thank you so much for tonight. I don't have anything else for you. I hope it all made sense, and I will look forward to talking with you more on Thursday. Thursday, we're going to talk about linear independence, section 4.5. I will see you then. You're welcome.
Now I can.
You had